You put the top on the table, it falls over. You twist it, you give it spin, and the top is stable. So spin angular momentum has the property of stabilizing things. This is the basic idea behind inertial guidance systems. In inertial guidance systems, you have a spinning wheel. At least in the days that the guidance systems had mechanical wheels. But that spinning wheel is mounted in such a way that you cannot put a torque on the axis of rotation of the spinning wheel. That's the way it's mounted. We call it three-axis gimbaled gyros. So the moment that you put a torque on it, the housings, in this case the yellow and the black housing, will start to rotate. And you never manage to get that torque on the spinning wheel. You never get it on this axis. And therefore, if now you put it on your boat or you put it in a plane, a missile for that matter, if you can never put a torque on the spinning wheel, and if the angular momentum for spin is in this direction, it will stay there forever and ever. It will stay there forever and ever, assuming that we have no frictional losses. And if then the plane turns, the direction of the spin angular momentum will not change. And if then the plane turns, the direction of the spin angular momentum will not change. But what will happen, of course, is that this yellow frame will rotate, or this black frame will rotate. And in these bearings here are shaft encoders. And they sense the rotation that the outer housing makes in order to keep this thing pointing at the same direction. And that signal is being fed back to the automatic pilot, and that keeps the plane flying in the direction that you want to. So you use as a reference all the time the spin angular momentum of your gyro, which is now mounted in such a way that you cannot put a torque on it even when the plane changes direction. And I want to show that to you. Okay, this is the direction of my spin angular momentum. And I'm the airplane. And I'm going to fly. Look at that spin angular momentum. It has no respect for me. It stays in the same direction no matter how I fly. It stays in the same direction no matter how I fly. And the error signals that come from the bearings of the yellow housing and the black housing, those arrow signals are fed back to the automatic pilot, and so the plane will stay on course. Now what I can do for you to come to a final test on your thinking, this wheel is suspended in such a way that there is no gravitational torque on it, like there was here. But I can put a torque on it by simply putting some weights on the axis. And what do you think will happen now if I put some weight here on the axis? So the wheel is spinning, but now I'm going to put a torque on it here. It is spinning in this direction. Angular momentum is pointing straight at me, away from you. I'm going to put a torque on like this, putting a weight there. Torque will be in this direction. What will the spin angular momentum do? Torque is in this direction, spin angular momentum is in this direction. Spin angular momentum will start to chase the torque. Watch it. There it goes. The spin angular momentum is chasing the torque. You see exactly the same thing that I've shown you before. And if I make the torque higher, then the precession frequency will go up. See, it stops now immediately when I take it off. Put it back on again. Continues. Put more on it. Goes way faster. What happens now if I put the weight on this side? So I change the direction of the torque. If I put it on this side, torque is now in this direction, spin angular momentum is in this direction, it's going to reverse direction. There we go. And you see it does. Amazingly non-intuitive. If you have problems with this, you're not alone. If you have problems with this, you're not alone. See you Wednesday.
So you should already know that this is a vacuum-powered instrument. So obviously in the back here, we're going to have a vacuum line in, and then we're going to have air inlet. So the vacuum is actually pulling air out, and then air is flowing in, usually through this little filter here, some sort of filter there to make sure it's clean air going into the instrument. And of course this one's had a little bit of a rough life. We have our little knob that adjusts the horizon line up and down for us, so we can configure it based on what attitude the aircraft's flying at. And if we take all that off, we get to our glass and our little O-ring, because of course this entire instrument is under vacuum, so it's totally under suction on the inside there. And if we go ahead and pull this guy out the back, we'll get to the inner workings of the instrument. So for starters, looking at the face here, we can see that we obviously have the pitch component of this, and then we have a roll component. So the way this instrument is set up, it can actually roll a full 360. Of course, that would be quite a wild ride. And then we have a limited pitch component. So we can see that if we tilt this gyro here on the inside that I'm holding with my right hand, if I start to tilt that, I get to a max of about 20 degrees nose down. And if I tilt it even more, you don't see the actual face of the instrument moving at all. So although the instrument knows that you're tilting more than 20 degrees, it limits the indication to about 20 degrees or so. Now if we were to go even farther, say we were trying to do a loop, that's when our gyro would hit its limit. And when the gyro hits its limit, that's when the instrument tumbles and gives us really bad information. So during a spin or during loops and things like that, gyro instruments do not indicate so well because they don't like doing spins like that. So to take a closer look at this, we said we have air flowing in through here, vacuum pressure, suction right here. So this entire instrument, everything in here is under suction. So air is being pulled out of the instrument, coming in through there, in through here, through this arm right here, into the little gyro housing. And if we rotate that over there, and we remove these little limiters, we can then go ahead and take a look at the actual gyro inside the instrument. So this is what actually spins around inside there. That big spinning brass weight is what gives it rigidity in space. Obviously it has to spin pretty fast, thousands of RPM, to really have any sort of gyroscopic effect and create that rigidity in space. So since we have air pressure flowing in through here, coming through this arm there, into the instrument, then there's sort of some cuts in that brass weight to make the airflow as it flows around there. The airflow is actually coming in through here, and then exiting through these little slots here to the rest of the instrument that's under suction, and then going out the back of the case. Now, to see this work a little bit, we'll go ahead and use our handy Dyson to create some suction and see just how fast we can spin this gyro. And now the gyro wants to remain rigid in space. So as we turn the airplane and rotate and bank it and pitch it, it wants to remain rigid in space, giving us good, accurate indications as to where we actually are relative to the horizon. You can see that if I actually try to turn the instrument, that gyroscopic precession converts any sort of turning motion, 90 degrees in the direction of rotation, actually makes it want to pitch. So that's why if there's any sort of resistance in the instrument, it's not going to indicate accurately. It needs to be nice and free, moving around that axis with very nice precise bearings. Movements in the aircraft, say like actually do a full loop, you can see that the instrument's not going to be too happy, and it's going to start giving us very strange, odd indications. That is when an attitude indicator tumbles from making aggressive pitch or bank inputs. Now take a look at what the gyro actually looks like. As we pull it out here, you can see those slots on the sides, and what the idea is there is that as air flows through the air inlet, like we said, through this armature here, into this chamber through that little opening there, this little hole on the side there,